So now we're going to move on to discuss various hydration reactions of alkynes, starting with Mercury-2-catalyzed hydration, where mercury is the electrophile. And recall that this is going to be in category B, because mercury is a large atom that has at least one lone pair. So hydration, of course, means the addition of water. Hydrogen will add to one carbon of the alkyne, OH or hydroxyl will add to another. And mercury is going to be a catalyst, which means it's going to increase the reaction rate. We'll find that it makes the alkyne very electrophilic, and it's going to be regenerated in the end, or we're going to show in the mechanism that is not stoichiometric. The mercury is not consumed. Therefore, you would not have to use the full equivalent of mercury. One mercury ion can catalyze the reaction for multiple alkyne starting materials. The intermediate for everything in category B, just like oxymercuration of an alkene, will be a bridge intermediate or a mercurinium ion. In this case, there's going to be some alkyl group. The pi bond of the alkyne, or one of those pi bonds, is broken. Mercury will be attached to a single ligand, L, and will have a formal positive charge. And that bridge intermediate, right, can be described by drawing various resonance forms, but recall that more substituted carbon has more electrophilic character. And so the nucleophile, which is water, is going to attack that carbon that is more electrophilic. In other words, the regio selectivity is going to be Markovnikov, as opposed to anti-Markovnikov, which we will talk about in a different lecture. So let me show you the mechanism. There are various sources of mercury 2. So mercury sulfate is one of them. Sulfate is 2-, mercury is 2+, so those dissociate in solution. And I'm just going to keep it very generic because you could have multiple counter ions or ligands bound. So I'm going to use ligand L, where that ligand could be water, it could be sulfate. But the alkyne is going to attack mercury. One of the ligands is going to leave. And then the lone pair at mercury is going to attack back to form a bridge. So this gives us a bridge intermediate, where we now have a carbon-carbon double bond and a 3-membered ring or a mercurinium ion that is positively charged at mercury. So mercury only accepted one pair of electrons, but it donated 2, therefore it's going to be positive or electron deficient. The solvent water is abundant, and water is going to attack fastest at this most substituted secondary carbon that has electrophilic character. So when it attacks there, it'll do so in an anti or a stereospecific manner, so that the water molecule is trans to the mercury with its ligand, and cyclopentane is pushed upwards, where the positive charge lands on oxygen. So now, to alleviate that positive charge, another water or any base in solution is going to deprotonate and deliver a lone pair back to the electrophilic oxygen. And now we get to this intermediate that's known as a mercurinic enol. So the next goal is going to be to relieve the substrate of the catalyst, okay, or to regenerate the catalyst in solution. And what we have just made here is our acid, hydronium. So that acid, right, we are in an acidic solution, we already knew that from sulfuric acid, is going to protonate an alkene, right? Alkenes form carbocation intermediates when treated with strong acid. And that carbocation will form fastest at the secondary position here, adjacent to the oxygen. Okay. And the reason why that is fastest is because this is resonance stabilized. I'm going to depict the ring as R and show an additional resonance structure to explain this regio selectivity. Okay, this carbocation is secondary, right? It has two carbons attached. This oxygen does not count as carbon, whereas the other carbon is primary. So that primary carbon had one hydrogen here, and now I've added a second hydrogen, and so this is now a CH2. And the regio selectivity is reinforced by the fact that oxygen can donate a pair of electrons and stabilize this cation via resonance, or this is a full octet resonance form. So the most important structure is actually the one at the bottom here, where all atoms have 8 electrons. When the oxygen has 2 lone pairs, then the carbon here does not have a full octet because it only has 3 bonds. So to get to the enol product, we're going to regenerate that catalyst. And that's going to be done by what's called an elimination reaction, where the carbon-mercury bond breaks and the electron density goes into what was the carbocation or the MTP orbital. And this gives us an enol product. So this enol product is named because it has 2 sort of functionalities that have been combined. Alkene, right? And alcohol. But when they are in conjugation with one another, okay, there's delocalization here. They are no longer 2 separate functional groups, right? But the electronics of them are different than alcohol or an alkene alone would be. So this is named an enol. We are going to find that that's the immediate product of Markovnikov hydration, where we get this secondary enol because water attacked that more substituted carbon. But the enol is not the final product. So that enol product goes on to do something else and isomerize in this same solution. So I'm going to take the enol that we made and show that it's still in strong acid with water present. And in the least bit of acidic or aqueous acid or aqueous base, enols will tautomerize or isomerize to another more stable form. And it should make sense to you that an enol, just like an alkene, is a nucleophile. It's actually a pretty good one. And it's going to protonate with strong acid to create a carbocation at the most substituted carbon. Once again, this carbocation is stabilized not just by hyperconjugation, but also by resonance, where you can show pi bonding between C and O and delocalize the charge. And right, we go from one resonance form to the other by pushing a lone pair down into the MTP orbital, and this is the most important and full octet resonance structure. After we do that protonation step, now we do deprotonation, where water, the conjugate base, deprotonates to give the ketone product. Okay. So this is a ketone, or it's a carbonyl with carbons on both sides of the carbonyl. And the tautomerization overall is just this, where the carbon-carbon pi bond okay, via protonation becomes a CO pi bond. And the hydrogen that was acidic and on the enol is now a hydrogen at the alpha carbon. So you swap the location of the hydrogen and the pi bond. And the carbonyl, this is favored. So this is what you're going to draw as your major product. So the carbonyl side, in this case, the ketone, is the more stable product. And that's generally true for most carbonyl compounds because C double bond O is much stronger than C double bond C. It takes 175 kcals per mole to break C double bond O, but it only requires 145 kcals per mole to break C double bond C. So the equilibrium favors the ketone. But overall, tautomerization is just protonate, draw a resonance structure, which is not a step, right? It does not take time, but we just draw the resonance structure to remember that this pi bond can develop. And then we deprotonate. And we want to make sure that if there's any charge at all for the intermediates, because we are in an acidic solution, we use positively charged intermediates because we have an excess of H plus. So I'm going to talk a little more about this tautomerization. So if you have a ketone, that means there are two what's called alpha carbons, or carbons that are one away from the carbonyl, and those have protons that are acidic, as we'll learn later in Orgo 2. So those are two distinct sets of alpha protons there. And if you want to think about two different tautomers, right, or enol tautomers of this ketone, then one way to do it would be to remove the red proton and show the enol between carbons 2 and 3, or you could remove the purple proton and show the enol between carbons 1 and 2, where the red proton essentially has been removed and we have protonated the oxygen. Here, the purple proton has been removed and we've protonated the oxygen. And remember that this is the most stable because the carbonyl, or C double bond O, is such a strong bond. But if you had to decide what the second most stable one is, it would be the more substituted alkene. So this enol on the far left, from removing the red alpha proton, is going to be the second most stable. And the least stable is the carbon-carbon double bond that is least substituted. Okay. So if you start with an alkyne and add mercury and water and acid, you have to decide if it's going to be regioselective or not. In other words, this alkyne has two secondary carbons. Both carbons 2 and 3 are secondary. So it is not regioselective, right? It's an asymmetric internal alkyne. So what that means is upon hydration, we're going to take it down from a triple bond to a double bond. And the OH with the enol could form at the secondary carbon 2 or the secondary carbon 3. Okay, you get about 50% of each of these enols. It is not regioselective. And then those would each tautomerize to a more stable ketone tautomer. So after tautomerization, you would have about 50% of 2-pentanone and 50% of 3-pentanone. So asymmetric internal alkynes give mixtures of various ketones upon oxymercuration or mercury-catalyzed hydration. Okay, so another type of question you could see is retrosynthesis, where you're asked to give the starting material. And what I do for this is I think backwards, well, what are two possible enols that I could have had here? Okay, so there's alpha carbon with an acidic proton on each side. So maybe I could have had two different enols possible. So one would be here, and the other would be there, where in the left compound we have removed the red alpha proton from the tertiary carbon and replaced that with a carbon-carbon double bond. In the right compound we removed the primary. So then I want to think about, well, what is the alkyne that these are going to derive from? So retrosynthetically, think backwards one more time, try to draw an alkyne for this, it's not going to work. Okay, you cannot hydrate this. So there's no hydrogen on this carbon. So this could not have come from hydration. In other words, this is a pentavalent carbon with too many bonds. Which means you can't have an alkyne there at that tertiary center. But if you think backwards from the other one, you could have a terminal alkyne here, okay? And you've added the H to the primary carbon and the OH to the secondary carbon. So this enol could come from hydration of the terminal alkyne. So this is what we want to start with. So I'm going to redraw that terminal alkyne here. It's optional whether or not you show this acidic proton. It's not reacting this mechanism because it's in an acidic solution. And you add some mercury 2 source that is not stoichiometric and it's catalytic, along with water and a strong acid like sulfuric acid. And it would go through the same mechanism that we did on the first page. Okay, so the next question is asking about regioselectivity. So which of the following ketones could come from regioselective mercury-catalyzed alkyne hydration? The first thing you should do to think about whether or not it would have been regioselective is just go back and draw the possible enols. So this one could have come from an enol at carbon 2,3 or an enol at carbon 1,2. And one step backwards, we could form the enol from having an alkyne between carbons 2 and 3, or form the enol from having an alkyne between carbons 1 and 2. So if you start with this one here, okay, there is one secondary carbon and there is one primary carbon. So that would be regioselective. Okay, you would not want to use this route where there are two secondary carbons because that would not give you a single product. It would give you a mixture of products. So for the next one, there's a single enol because it's symmetrical, and therefore this enol would have to be formed from an alkyne between carbons 2 and 3, and for the same reason, this one cannot be regioselective, just like that same compound I drew at the far left, because both these carbons are secondary. So far, this one works if you go through the terminal alkyne path. But this one would come from an internal alkyne, so it will not work. If you think backwards here, the enol would have been conjugated with the benzene ring, and before hydration, the alkyne would look like this. And even though this one is internal, right, both carbons are secondary, this would be regioselective because this is benzylic. So it's better stabilizing positive charge, and water will attack there. The oxygen or OH will end up there, and eventually the ketone will end up at the benzylic position only in the product. And the last one is cyclic, which is going to be a problem. It would come from a cyclic enol, which is possible, but if you try to think backwards from there, you'd have to have a triple bond in a ring, and that's very unstable. This is called a cycloalkyne, and this is too unstable to be isolable at room temperature unless the ring is 9 members or larger. 6-membered rings do not form stable alkynes at room temperature. So this one is not possible because the starting material does not exist. Okay. So the final problem here is sort of an application where we combine bridge intermediates from last video with tautomerization from this one. And you guys know that the alkyne is a nucleophile. It will attack the electrophilic bromine and break the long, weak bromine-bromine bond. And bromine is a large atom with multiple lone pairs, and so it's going to form a bridge intermediate. And that bridge intermediate is differentially substituted, where this more substituted carbon has more electrophilic character. And therefore, the nucleophile, water, because it's the solvent, and it's far, far higher in concentration than bromide, that water is going to attack the more substituted, more electrophilic position and give us this anti-addition product where water and bromine are trans across the alkyne. And next, deprotonation is going to give a neutral enol. Where another solvent molecule can retrieve the acidic proton and give a lone pair back to oxygen. So you get this bromoenol here. Remember, enol means alkene right there, conjugated with alcohol. And what happens is that enol is going to tautomerize to a ketone in the product. And this tautomerization is mediated by the hydronium that we just made by deprotonating that protonated enol. And alkenes with strong acid are going to form carbocations. So it's no surprise that this enol, just like any other alkene, is going to protonate in strong acid. and there are 2 lone pairs of oxygen. All right. The secondary carbon is going to bear the carbocation because the primary carbon is less substituted and does not have electron donation from the oxygen. So the oxygen can donate a lone pair in here to show that this carbocation is especially stable because it's stabilized by this full octet resonance form. So we protonated first, drew a resonance structure, had positively charged intermediate, and then we deprotonate to reform our catalyst. This is remaking hydronium to give the alpha bromo ketone product. Okay, so that is a problem that puts it all together, where you recognize that bromine is a large electrophile, that it's going to form a bridge intermediate. That bridge is more electrophilic at this more substituted carbon, so water attacks there. Water is more abundant, so it's the more likely nucleophile. Deprotonation gives a neutral bromo-enol, but enols are unstable and they have more stable, So this enol is unstable and it has a more stable ketone tautomer. Enols will tautomerize in strong acid, which we just made, by protonating an alkene. And protonation of an alkene gives a carbocation intermediate. Right? Carbocations can be stabilized by both hyperconjugation and by full octet resonance structures. And finally, deprotonation regenerates that hydronium catalyst so that after this 2-step tautomerization, you get the more stable ketone product, which is more stable because C double bond O is so strong compared to C double bond C. So in the next video, we will talk about an anti-Markovnikov way to do this hydration. But you can find more practice with alkyne hydration in Unit 2 of my Orgo 1 course guide and in Unit 1 of my Orgo 2 course guide at chemguides.com.